All right, this is the review problems for Unit 6. All right, so the first problem says we have a potential difference between two plates of 520 volts. And it wants to know what's the strength and direction of the electric field of the two plates for part A. So we have several formulas for electric field strength, but the one that I would use on your formula sheet for this problem is it tells us that the potential difference is equal to the electric field strength times the distance between the two plates. It gives us the potential difference is 520 volts, and it also gives us the distance between the two plates in the problem of 0.8 centimeters, so 0.008 meters. So we can just divide both sides. That gives us the electric field strength of 65,000, and that's newtons per coulomb. It also wants to know the direction. The direction is the direction a positive test charge would go, so that'd be down. Because if you look at that diagram that it gives you, it has positive charges on the top plate, and it's got negative charges on the bottom plate. So the direction a positive charge would go would be from positive towards negative. So we would say down for the direction. Okay, then part B wants to know how much work is required to move one more electron to the negative plate. So we want to know work required to move one electron. That formula is on your formula sheet. It is the potential difference is equal to the work required to move a test charge divided by the charge of that test charge. So we know the potential difference is 520, and we can find then the work required to move an electron using the charge of one electron, which is 1.6 times 10 to the negative 19 coulombs off your formula sheet. Multiply both sides by the 1.6 times 10 to the negative 19, and you get the work is 8.3 times 10 to the negative 17, and that's in joules. Okay, the next question says a positive test charge is moved 5.6 centimeters against an electric field, and they gave us the strength of the electric field of 75 newtons per coulomb. And they say through what potential difference has the charge been moved? So we're looking for the potential difference now. And we have a formula that relates those quantities. We just used it in the last problem. It's the potential difference equals the electric field strength times the difference between the two plates. So we're looking for potential difference in this case. We're going to use 75 for the electric field strength. And for D, we got to move the decimal place over and use 0.056 meters. That gives us 4.2 volts. 3 says how much voltage is required for a capacitor with a capacitance of 0.75 microfarads to store 2.3 microcoulombs of charge. So this is going to be the charge on the capacitor. So this is the relationship off the formula sheet we're going to use. We know the charge is 2.3 times 10 to the negative 6, and we're looking, the capacitance is 0.75 times 10 to the negative 6, and the charge up here is 2.3 times 10 to the negative 6. We can then find the potential difference or the voltage by cross multiplying, in which case we just need 2.3 divided by 0.75. That's about 3 volts. 3.06 repeating. Next question is 4. 4 says a 9-volt battery is connected to a light bulb as shown. So let me quickly draw this as far as a circuit goes. So it looks like this. Part A asks how much power is delivered to the light bulb. Power equals IV. We know the voltage drop across this resistor has to be the same as the battery because they're exactly the same. So we're going to use power equals IV. I is 0.5, V is 9, so that gives us about 4.5 watts. Part B then says how much energy will the bulb use in 1 hour? Well, 4.5 watts is really a joule per second. So if we want to know 1 hour, we're going to multiply that by hours. There's 3,600 seconds in an hour. So convert 1 hour to seconds first. And the seconds will cancel, and we'll get 16,200 joules of energy. Okay, last question, part C then says how long would the bulb have to stay on to use 1 kilowatt hour of energy? All right, for this, I'm going to use power equals energy over time. They gave me the amount of energy right here, which is we're going to use 1 kilowatt hour. And we're looking for time. And we have the power rating of our bulb is 4.5 watts. So we have 4.5 watts equals energy over time. Now, I have to convert this to watts though because I'm using watts on the left side, or I have to convert the power rating of our light bulb to kilowatt hours, one or the other. But kilowatt hour is just a unit of energy. So we can convert that really easily. 1 kilowatt hour is 1,000 watts times hours, which let's do 3,600 seconds instead. So a watt is a joule per second. And when I multiply by 3,600 seconds, this gives me joules. So it's, add 3 zeros here. It's 3.6 million joules. That's what a kilowatt hour of energy is. So that's what I'm going to enter in right here. All right, and all I need to do then is cross multiply. I basically need to take the 3.6 million and divide by 4.5 to find the time here, and that gives me 800,000 seconds. Okay, the next is problem 5. 5 says a 100-watt light bulb is turned on for 2/5 of the time for 30 days. So we've got 2/5 of 30 days for the amount of time that this is running for. And it says the price is 0.09, so 9 cents per kilowatt hour of energy. How much does the light bulb cost to run for 30 days? So we're going to run it for 30 days. All right, so let's multiply the 2/5 times the 30 days. 5 goes into this 6 times, so that's going to be 12 days total. Now, we have a power of 100 watts. All right, so let's use power equals energy over time. We know the time is 12 days, but let's convert that to seconds. That's 1,036,800 seconds if you convert. And we also have the power as 100 watts of our light bulbs. That allows us to find the energy. So let's multiply this number by 100 and we find the energy. Okay, so that should be 103,680,000 joules of energy. Now, here's our conversion that we're going to use next to figure out the cost. So now we know how much energy we have, but we're going to do the cost per kilowatt hour of energy. So let's convert this joules to kilowatt hour of energy. I do have on the formula sheet the conversion between 1 kilowatt hour of energy and the joules, and that's 3.6 times 10 to the 6th. So that'd be 1 kilowatt hour of energy equals 3,600,000 joules. That way the joules cancel, and I get the energy in kilowatt hours. 28.8 kilowatt hours. Now I can just convert using the rate that they gave us for cost, which is 0.09 per kilowatt hour. Kilowatt hours cancel, and when you multiply by 0.09, you get about $2.59, $2.59. Okay, the next question is 6. It says a current of 0.85 amps is measured through a 27 ohm resistor for 1 hour. I'm going to write 3,600 seconds instead. How much heat does the resistor generate? We have some different equations for thermal energy, but we want to use one that gives us that has current and resistance. So that's power equals I squared R. And we're asked for the heat, so we're asked for thermal energy in this case. Power is energy over time. So the equation I actually gave you in the notes for thermal energy is I multiplied both sides by time. And that gave us the thermal energy equals I squared R times time. I squared is 0.85 squared. Resistance is 27 ohms times the time is 3,600 seconds. And that gives you your answer in joules, 70,227, and that's joules. All right, next question number 7 says the long distance high tension wires use 500,000 volts. First question, what is the power output of these wires in watts, kilowatts, and megawatts if the current is 20 amps? So power equals IV in this case, so we're going to use 20 times 500,000, and that's going to be in watts, which is 10 million watts. And they also want the answer in kilowatts. So if I move this over 3, I'd have 10,000 kilowatts. And then if I move it over 6, I'd have megawatts. So move it over 6 and you get 10 megawatts. All right, so then question B asks, what is the power dissipated if the wires have a resistance of 0.015 ohms? So for that, let's use this resistance, and then keep in mind that the voltage is 500,000. So we're looking for a relationship for power between R and V, and that should be on your formula sheet. So that's 500,000 squared divided by the resistance, which is 0.015, and that gives us, all right, and this gave us an outrageous number, and so we can't use this formula because the voltage between any 2 points is basically 0 because they have the same amount of energy per charge at this point in the wire as they do here. So this number would be a lot smaller. I can't use 500,000 for that. That's not going to work. But what we can do is, since we know the current in this case is 0.015 ohms, I can use resistance and current because power equals current squared times the resistance. So if you do, I'm sorry, the current was 20 amps. So if we do 20 squared times 0.015, that gives us 6 watts. Okay, the next problem gives us a circuit like this. 2 resistors in series, 1.2 amps of current running through. Wants us to find the resistance of both resistors. We can use V equals IR on this resistor, where we know the current's 1.2 and we know the voltage is 5.4 across it. In order to find R, just divide both sides by 1.2, and that gives us 4.5 ohms. Next, if you do the same, you get about 8.2. To find the equivalent resistance for the circuit, you add them up and you get about 12.6 repeating ohms. Okay, for the next problem then, we've got a 120 volt battery, 88 ohms here, and then 2 12 ohm resistors in parallel. The first question wants us to find the current in the circuit. I'm sorry, the equivalent resistance of the circuit. So first we're going to add up these two in parallel. If you do that, then you get equivalent resistance of these two in parallel equals 1 over 12 plus 1 over 12, which is 2 over 12. And if you flip both sides of this equation, you get the equivalent resistance equals 12 over 2, which is 6. So basically I can rewrite this circuit to look like this with 188 and 1 6 ohm resistor. Like this. And then you can just add them together to get 94 ohms of total resistance in series like that. So there's the equivalent resistance of the circuit. From there we can do V equals IR using 94 here and using the total resistance 120 to find the current of the circuit. So just divide 120 by 94, which is about 1.28 amps. So then we have 1.28 amps going through right here. So if we figure out what the voltage drop is across this resistor, we'll figure out how much is left for the last two. So to do the voltage drop across this, you do V equals IR. We know the current's about 1.28 and the resistance is 88. That gives us a voltage of 112.3 volts. So then if you subtract, you get about 7.7. So that means there's about 7.7 volts left if you subtract from 120 to fall across these two resistors. Another way to do it is if you know the current is going through at 1.28, half the current goes here. So half of 1.28 would be the current here, and you could just do V equals IR, where you take this half the current, put it in for I, and multiply by 12. That should also give you about 7.7. Okay, so for problem 11 here, they told us this information. So if we know that this is 4 volts here, then we know this has to be 5 volts because it has to drop a complete 9 volts. So we can use this information to find the current going through the circuit. If you just use V equals IR on this resistor right here, you have 5 volts equals I times 24. Divide both sides by 24. That gives you about 0.2 amps. So now use V equals IR again, where you know this is 0.2. You're looking for the resistance and you have the voltage is 4. That gives you 20 ohms of resistance. Okay, next problem I drew a little differently than the diagram, but we're trying to find the resistance of this resistor. So we're first going to add these two together up here in parallel. To do that, you get this, which I can make 2 over 30. So that'd be 10. If you cross multiply or solve, you do 10 ohms. Up to here, use V equals IR for the total here. And find the equivalent resistance for the circuit has to be equal to 37.5. And then you can set the equivalent resistance for the circuit has to be equal to 10 plus these two in parallel, which I don't know what that is. So I'm going to call that X. Now the equivalent resistance for the circuit we found was 37.5. So we can do 27.5 has to equal my resistance for the circuit here. It would be 27.5 right here. And now I can solve this for R3, which gives you about 80.